After having enjoyed robots crashing into each other, or almost, we need to come back to reality and ask ourselves, what if robots cannot see each other? What if this famous flow of information that seems to support networked control fails to exist? What does flow of information even mean? Graph theory is the subject for this new episode of Networked Robotics. In our second episode, we introduced our first algorithm, the rendezvous protocol. This protocol is constructed on one of the central equations in networked robotics, the consensus equation. According to the consensus equations, robots move towards the center of mass of those robots they can measure the distance from. We call these robots neighbors. The concept of neighbors plays a fundamental role in the equation itself. In fact, it's by measuring the distance that robots share the information. At the end of our second episode, we ask an apparently simple question. How would the consensus equation work if robots cannot see each other? Today, we will try to understand how to describe and how to use this concept of flow of information that seems to be so important for the consensus equation and for networked robotics itself. First of all, how does information get transferred in the real world? Well, depending on the information we care about, there could be many possible frameworks that enable and allow its flow. We call these frameworks networks. For example, emails move through the internet, traffic moves through the roads, and respiratory disease moves through the droplets released by an infected individual. In order to formally describe and study these kind of processes that involve some flow of quantities between discrete locations, mathematicians use the idea of graphs. So our first question is, what is a graph? In order to study how information flows on a network, we need a level of abstraction, where we can produce formal results. The discipline that formally defines rules and tools to describe how a certain quantity, for example information, moves across a discrete group of locations or individuals is graph theory. Somewhat, not too surprisingly, the main subjects of interest in graph theory are graphs. A graph is an object composed by two ingredients. The first ingredient is a list of nodes or vertices, which we graphically represent as dots. We denote the set of vertices with a capital V. The second ingredient is a list of edges, which we graphically represent as lines between some pairs of nodes. The list of edges is a set of node pairs, and we denote it with a capital letter E. Not all nodes need to be connected by an edge, and we call a pair of nodes connected by an edge neighboring vertices or neighbors. For example, the set of nodes and edges for the graph in figure are the ones shown here. In addition, the neighbor set corresponding to node 1 is composed by the nodes 2 and 3. Edges of a graph can have directions. In this case, we refer to them as directed graphs or D-graphs. Graphs containing directed edges are called directed graphs. We call them undirected graphs otherwise. We can graphically represent the direction of an edge with an arrow. Undirected edges can either be represented as lines with arrowheads at both ends or just as simple lines. In addition, when we write an undirected edge as a pair of nodes, the order of the pair is irrelevant. On the other side, directed edges are denoted by ordered pairs of nodes. The node connected to the head of a directed edge is the head node, while the other is the tail. In addition, a path is defined as an ordered sequence of vertices that are connected by an edge. For directed graphs, the path needs to respect the direction of the edges. This is an example of how to write an edge as a pair of nodes depending on the direction of the edges. An important property of a graph is whether all its nodes can be reached regardless of the choice of the starting node. We refer to this property as connectivity. We say that a graph is connected if there exists a path from every node to any other node. For directed graphs, there are actually two possible interpretations of this definition, so we actually have two definitions. We say that a directed graph is weakly connected if by ignoring the edges' directions, we can create a path from every node to any other node. In addition, if we can also create a path from every node to any other node while respecting the direction of the original edges, we say that the graph is strongly connected. Finally, we can see here some special graphs that we will use in the future of this series.
From the discussion we had so far, it does look like graphs are really interesting quantities for representing a transfer of information between discrete points, for example, robots. There is, however, a point we should clarify before moving forward. Given a number of robots, for example, in a field or a number of robots in space, what is the graphs that connects them? Or, in other words, what makes two robots neighbors? The answer to this question depends on the technology the robots are using to transfer information. On one side, robots could transfer explicit messages between them, for example, through light pulses or through internet or through radio communication channels. But transfer of information between robots could also happen through sensors, for example, depth sensors based on infrared technologies or LiDARs, but also cameras belong to this category. Regardless of the particular technique used by the robots to transfer information, we can define models that abstract the details of the interactions between them, but can still capture the physics of the problem. For example, given that real-world sensors have finite range, we can construct graph models that define neighboring relationships based on the separation between robots. We call these types of graphs proximity graphs. The simplest possible model of proximity graph is the delta disk graph, where robots are neighbors, that is, can transfer information if their distance is less than a threshold delta. In this example, a team of robots is moving between random points. The lines projected on the floor represent the delta disk graph that exists between the robots at any given time. As we can see, this graph changes over time as robots move. Another possible choice of proximity graph is the Gabriel graph. In this case, two robots are neighbors if there exist no other robots inside the circle whose diameter is defined by the two robots themselves. In the second example, we can see a Gabriel graph between robots moving between random points. In addition to this, there are other possible types of proximity graphs, which we are going to encounter in future episodes. Now that we have some realistic model for generating graphs between robots, we can run the same experiment we ran in our second episode, assuming robots are connected through a proximity graph. Let's, for example, consider robots connected through a Gabriel graph. We can observe that as the robots move, the graph itself changes over time. And here is the case with the delta disk graph. We notice that in both cases, the graph changes over time. In addition, even though the starting conditions are the same, the behavior of the robots turn out to be very different if we change the way robots interact with each other. Now let's see another example. What happens if we reduce the value of delta to a very small number? In this example, as one would expect, robots that are not connected to anyone cannot move. This example is interesting because we can start to appreciate why graphs are so important in network robotics. We started this episode by saying that we need a formal way of defining neighboring relationship between the robots. If we take a group of robots, we know that there is a consensus equation that can be used to move them together. But where does really a graph come into place in the consensus equation? In order to answer this question, we need to introduce some quantities that can be manipulated using mathematical operations. Those quantities are matrices. The tools that we are going to look at now are used to represent graphs in terms of objects we can manipulate using mathematical operations. The branch of graph theory that studies this object is called algebraic graph theory. Let's take a look again to the consensus equation we derived 2 episodes ago. From this equation, we can see that the velocity of robot I depends on the relative distance from its neighbors. We want to figure out now if there's a way to remove this sum operator and represent the dynamics of the entire team with a single equation. This will allow us to make some important connections between what happens between the robots that execute the consensus equation and the underlying graph that exists between them. Let's consider an undirected graph G with n nodes, and let's define some quantities relative to it. The first quantity we define is the degree of a vertex. For each node in the graph, the degree of node I is a positive integer equal to the number of neighbors connected to node I. We can also say that the degree of a node is the cardinality of its neighbor set. Starting from this definition, the degree matrix is a square diagonal matrix of size n, and the element corresponding to column I is the degree of node I itself. The second matrix we introduce is the adjacency matrix. For a graph with n nodes, the adjacency matrix is a square matrix of size n, where the element ij is equal to 1 if there exists an edge between I and j. For an undirected graph, the adjacency matrix is always symmetric. For the graph in the example here, we can easily compute the degree and adjacency matrix. The final matrix we introduce today is the Laplacian matrix. One way of defining the Laplacian of a graph is through the difference delta minus A, where A is the adjacency matrix. Let's see an example of how to compute the Laplacians of a graph.
To better understand how to compute the Laplacian of a graph, let's have a look at the simple example. So as you can see here, this is an undirected graph with 4 nodes. So let's start by computing the degree matrix for this graph. As you can see, node 1 has 1 neighbor, which is neighbor 3. Node 2 has 2 neighbors, which are 3 and 4. Node 3 has all 3 neighbors, and then node 4 has 2 neighbors. So let's start writing that down. So as we said, 1 neighbor, and we get 2 neighbors. Node 3 has 3 neighbors, and node 4 has 2 neighbors. And then we'll fill the rest with zeros. Next, we'll compute the adjacency matrix. So we're going to start by assuming that this is a simple graph, which means that a node cannot be connected to itself. So let's start by writing that down. From the simple graph assumption, we get 0 on the diagonals, and then we can start building from there. So the first row, we'll see who's connected to neighbor 1. So neighbor 1 is connected to neighbor 2, no. So let's put a 0 there. Is connected to neighbor 3, yes. Is it connected to neighbor 4? No. And next we'll look at node 2, then 3, then 4. So let's look at node 2 now. Is it connected to node 1? No. Yes to 3, and yes to 4. Node 3 is connected to all 3, so we can just fill in. And then node 4 is not connected to node 1, but it's connected to the 2 other nodes. So that is the adjacency matrix we get. Okay. And now we want to compute the Laplacian. So let's use the equation that we know, which is the degree matrix minus the adjacency matrix. And this gives us the following. So let's start by filling the diagonal. And then we'll put the negative ones. And then the rest is zeros. And this is it. This is how you compute the Laplacian of a graph.
In order to show why the Laplacian of a graph is important for the consensus equation, we'd start by removing the term xi from the sum. Since the term xi appears for each neighbor of node I, it is repeated exactly degree of I times. In addition, by leveraging the definition of adjacency matrix, we can convert the indexes j from being only those corresponding to the neighbors of I to the entire set of nodes in the graph. What we observe now is that we can represent the sum of the first line through the inner product between two vectors. The first on the left is the sum between the negative of a row vector of zeros with degree of I located at the ith position and a row vector formed by the elements of the adjacency matrix corresponding to node I. The second vector is the concatenation of the position of each robot. In reality, the position of each robot is a two-dimensional quantity, and this should be taken into account when writing this equation. Let's for now assume that this is just one component of the position, for example, along the direction x, and we can repeat the same procedure for the component along y or z in case of flying vehicles. The final observation is that because of the definition of the Laplacian, the vector on the left, in this inner product, is exactly the ith row of the Laplacian matrix. In conclusion, thanks to the convenient definition of the Laplacian, we can write a single consensus equation for all the robots in the team. We refer to these equations as the consensus equation at the ensemble level. The importance of the Laplacians in network robotics cannot be overstated. This is also the case for other disciplines that studies process that evolves across graphs, such as traffic control or computer networks or the diffusion of disease. In this course, we are not going to spend too much time developing the theory around the Laplacians, but it suffices to say that just by looking at the Laplacians, one can say really a lot of things about a graph. There is, however, one important fact we need to mention about the Laplacians, which is, by the way, the answer to the question we started this episode with. When does the rendezvous work? Well, it is possible to show that if the graph is connected, then the quantities of the process that is controlled to the consensus equation will all converge to the same value. This is the case, for example, of robots executing the rendezvous protocols. If the graph is connected between them, then they will meet at the same location. So this is it. Graph connected, robots go all to the same location. Well, this is it in theory, but in practice, as we will see, there are a number of considerations to keep in mind. Well, this was a lot of stuff today. A lot of definitions, a lot of new mathematical concepts, and many points to connect. So maybe some of you are thinking, do we really need all of this just to move a few robots?
When you go to networked teams of robots, it becomes tricky because all of a sudden you have to understand and describe the robots themselves and their dynamics. What are they doing? How do they move? But also the interconnections, meaning how is the team actually working together somehow? And you need to capture things like information flow or who can see whom. And that becomes easily rather daunting unless you have the right abstraction, the right kind of mathematical object that allows you to talk about these things, that kind of keeps the stuff you're interested in, like interactions, meaning can you talk to me, can I talk to you, without worrying about the details about the communication channel or what kind of sensor I have. And it turns out that the graph is exactly the right mathematical object. It ignores and hides the stuff we're not interested in and keeps the stuff that we are interested in. On top of that, if you have a graph, we can associate these algebraic objects like matrices, like the Laplacian, with the graph structure, and all of a sudden we can actually talk about the robots and their dynamics and the graphs using the same language of linear algebra and matrices and systems. And that is why the graph is exactly the right object for understanding networked multi-robot systems.
Over the course of today's episode, we were able to start from a simple protocol that is designed to move robots to a single location, all the way to very sophisticated mathematical tools that are used to describe graphs. So the question is, what's next? Well, as we will see starting the next time, we can use these very sophisticated tools, the Laplacian and the adjacency matrix, to represent other kind of protocols to move robots. For example, how to move them in a circle, how to assemble formations, or how to disperse them in the environment. Well, until then, don't forget to like and subscribe, and remember that all the codes that we use in these experiments is going to be available on the GitHub page of the Robotarium. See you next time.